Hello, so today I will be starting my lecture on atomic physics, and the first topic that I'm going to discuss is the photoelectric effect, which is Einstein's famous experiment that got us into the world of atomic physics. And so what Einstein did in the 20th century is he had a metal plate and he had two different lights. One was red and one was blue. When he shined the red light onto the plate, he couldn't see any difference in the current that was being induced in the two metal plates that he had, no matter how much red light he shined. However, when he shone the blue light, even the tiniest bit of it caused a current to be induced in the metal plate because electrons were leaving the plate and being liberated from their atomic shells. Now, we can see this on an atomic level here, how that would happen is that the light, the photons, they have a wave nature as well as particle nature, because they can be defined as waves or as particles, and the wave function of each of those photons goes into the atoms of the metal and helps the electrons be free from the atomic shells. And so we know that the energy required to release the electrons from the atom is defined as a work function, because you have to do work to make sure that electron exits out of that atom. And the energy that the photon possesses is hf, as we know from Planck's formula. Therefore, we can say that the kinetic energy of the electrons being emitted out of the plate is hf minus w, which is Planck's constant times the frequency of the original photon minus the work function required to liberate the electron. Now, some of you may be asking, how does this work function work? How do you find out how much work is actually required to liberate this electron? And that's what I'm going to explore next. Alright, so now we're going to look at what actually happens inside the atom in the photoelectric effect, and we can explain this using the Bohr model of the atom. Now, we know that the Bohr model has certain energy shells or energy levels for each of the electrons, which each possess a different amount of energy for the electron. The very bottom state, the one closest to the nucleus, is called the ground state, and any states above this ground state are called excited states, because that means the electron has gained some energy. Now, let's say that we had an electron originally existing in the second state, or the first excited state as you would call it, and it had an energy of 4 electron volts. Now let's say a photon with 4 electron volts came in and hit this electron. What will happen? Well, first we know that it requires 3 electron volts to jump from this energy level to this energy level, because we know that 7 minus 4 is 3. And so after it jumps here, we still have that 1 electron volt left over, and you say, oh, should it jump to, let's say, 1/4 or 1/3 of the next energy level? This is one of the things you have to remember, is that the electron can't do that, because everything in atomic physics is actually quantized, which means you can only have whole number integers of something. So you can only have a jump from the first level to the second level, or the second level to the third level. You can't have a jump, let's say, from the second level to the 2.5 level. The electron can only exist in n equals 2 level or n equals 3 level. And that's one of the things that's important. Now, next we'll look at one of the scenarios that happens is when the electron actually jumps down from the excited state and emits a photon, and how you calculate that. Alright, so now we're going to look at what happens when a photon is actually emitted, which happens when the electron in one of these excited states drops back down to a lower state, or the ground state. So let's say in this example we have an electron that is in this state, which has an energy level of 9 electron volts, and it drops all the way back down to the ground state, which has an energy of 1 electron volt. Now, how do we know how much energy was emitted in this photon here? Well, we can see delta EV, which is 9 electron volts minus 1 electron volt, and we know that the photon has an energy of 8 electron volts. Now, let's say it asks us to find the frequency. Well, we can do that easily as well using Planck's formula and find the frequency, and we know that it's 2 times 10 to the power of 15 hertz. Using this, we can also know that this is a UV ray that's being emitted in the photon, because we know that UV rays lie in this spectrum, and that's how we know what happens. Now, you have to remember that because these are quanta, again, same as if you were shooting a photon, at an electron, you have to remember that this electron can't drop to something like half a level or a third of a level, because they're quantized energy levels. So you can only drop to 1, 2, 3, or 4, or any whole number integer of levels. You can't drop to 1.5 or 2.5 levels. And so that's one of the most important things in atomic physics here, is that everything is quantized and you can't have half of something or a fourth of something. Now next I'll show you what a graph of this could look like, what a work function graph could look like, and what a kinetic energy graph of the emitted photon could look like. Now we're going to look at the relationship between the kinetic energy of the emitted electron and the frequency of the original photon hitting the metal plate in a graphical manner. Now we know that the formula for this graph should be Ek is equal to Hf minus W, as we calculated before, where Ek is the responding variable as we manipulate the frequency of a certain photon. And what we see here is that both the x and the y intercepts tell us very, very important things about this material. For example, the y-intercept here occurs when the frequency is 0. Now, when we have 0 frequency, that means this value would be 0, and Ek would just turn into negative work. So this actually tells us the amount of energy we need to liberate the electron out of the atom, and that's the work function here, which is the y-intercept. Now, the x-intercept here is very interesting as well, because that tells us that Ek will equal exactly 0. It won't be negative, which means the electron will not stay in the atom, and it won't be positive, which means the electron won't start moving after it gets released. This is called the threshold frequency, and that's the exact frequency of photon that we need to actually release the electron and make sure that the Ek is 0. So this threshold frequency is important for us as well, because it gives the minimum frequency you need to release the electron, not anything more. So it just gets released. It doesn't move after this. So this is very typical of a graph of what you could see between these two variables. Now let's say we change the graph. Let's say we had a graph, but the line instead was a bit higher like this. What that would mean is that the work function for this material would be actually a bit lower for this material, which means this atom holds onto its electrons less tightly than the material we looked at before. If this line was a little bit lower, let's say here, that means its work function would be higher, which means you'd need more energy to liberate that electron out of the atom's shell, because that material holds onto its electrons more tightly. And that's the basics of the photoelectric effect and how it works.